In this video, we're going to look at when function is differentiable. Differentiable means that you're able to find the derivative. When you're able to find the derivative, it means you're able to find the slope. So when function is differentiable, it means you're able to find the slope. And there are 4 cases where function is not differentiable, or 4 cases where you cannot find the slope. So let's take a look at first 2 cases. First case is when you have a corner. So let's look at the graph of f of x equals absolute value of x. Notice that the function is continuous, meaning that you could draw the line without lifting your pencil. However, when x equals 0, notice as you approach 0 from the left, slope is negative. But as you approach 0 from the right, slope is positive. As a matter of fact, the slope as you approach 0 from the left will be negative 1. Slope as you approach from the right, that is slope of absolute value of x, that is positive 1. So since they have a different slope, when you approach 0 from the left and from the right, it's not differentiable at x equals 0. The second case is when you have a cusp. This is a graph of x to the 2/3. And notice this graph is also continuous everywhere. You could draw the line without lifting your pencil. However, let's take a look at when x equals 0. When x equals 0, when you draw a tangent line at any point, it's going to be negative. What about you approach 0 from the right side? The tangent line at any point will be positive. So at cusp, there is no derivative or slope, or we say it's not differentiable. Let's take a look at the last 2 cases where function is not differentiable. The third case is when you have a vertical tangent. Here you have a graph of cube root of x, and it's continuous everywhere. But when x equals 0, notice as you draw the tangent line at x equals 0, you're going to get a vertical tangent line. And you know that from algebra 2 or pre-calculus, when the line is vertical, you have no slope. So at a point when you have a vertical tangent, that's when it's not differentiable. The last case is when you have a discontinuity. Look at this piecewise function. You are not able to find the derivative when x equals 0, because when x equals 0, it's not continuous. So when you have a discontinuity, there is no slope, or you cannot find the derivative. So let's take a look at f of x equals absolute value of x minus 2 plus 3. And where is it not differentiable? The best way to do this problem is graph the function, and whether we have one of those 4 cases where it was not differentiable. We could use our graphing calculator, but this is a simple graph using a parent function of absolute value of x. So it looks like we're going to move to the right twice, and everything's going to go up 3. So when you graph, you're going to go to the right twice, and everything moves up 3. So it will look something like this. Again, you could confirm it with your graphing calculator. Now notice, where is it not differentiable, this function? Well, you have a corner when x equals 2. So this function is differentiable everywhere except when x equals 2. That's how you write it. Differentiable everywhere except at x equals 2. So again, in order to do this type of problems, to see where it's not differentiable, the best way of doing it is graph. Graph the function if they don't give it to you. If they give you the graph, just look at the graph and see where those 4 cases occur. The last thing that I want to talk about is differentiability implies continuity. So if f has a derivative at x equals a, then f is continuous at x equals a. So in other words, if you're able to find the slope. If f is differentiable, then you could automatically conclude that f is continuous at x equals a. However, the reverse is not true. So for example, if f is continuous, then can you conclude that f is differentiable? No, not always. For example, remember the graph of absolute value of x? Absolute value of x is continuous everywhere. However, it's not differentiable at x equals 0. So the reverse is not true. So be careful with that.